So let's begin. So hello everyone. Today I have the great pleasure of introducing Professor Yunzhi Wang as today's EA seminar speaker. So Professor Wang joined Ohio State University in 1996 and has since been an expert in the theoretical modeling and computer simulation of microstructure evolutions. So Professor Wang has published over 240 journal articles, including over 100 academic materialia papers, and has definitely made some fundamental contributions to our field. So, and some of us may still remember he gave us a talk back in 2016, and today we are very fortunate to have him here again to present some of his new recent work in the computational micromechanics. So now, Professor Wang, please feel free to start whenever you are ready.
All right. Thank you very much for everybody to join me in this difficult time. And so I'm going to turn off my video as well and then try to avoid the traffic on the internet to make sure the things can go smoothly. Let's try to, can you hear me clearly? Can you see my screen?
Yeah.
Great. So today I'm going to try to show you some of our recent study on about during either structural applications or biomedical applications by microstructure engineering. And I think everybody are familiar with microstructure engineering in terms of control dislocations. But I'm going to show a little bit more, and I'm going to try to focus my talk on the coupling between deformation and phase transformation. So I think for any research, scientific research, the most important thing is to get some new ideas. And after you get the idea, then you can use whatever tools available for you. And if you think you go to the lab, do the real experiment, it can bring you to the answers faster. Then you good go and then do the experiment. If you think you can do virtually of the experiment by computer simulation, then you do the computer simulation. So this is not a critical. The critical is to have the kind of novel and the new ideas. So I'd like to start with the thank my co-authors. So this is most of the work done by my former graduate students and Jia Ming's joint students with Chongyi Zhang. And he spent a year at Ohio State. Tianlong, same thing. He spent some time and joined with Dong Wang from Xi'an Jiaotong University, and my longtime collaborator, Xiaobing Ren from NIMS at Japan. So this work is supported by the National Science Foundation and also the Department of Energy. So I want to show you that the plastic string carrier can be either dislocations or can be a structure transformation or can be a deformation twinning. So here I'm going to show you two animations. So the first one is about dislocation plasticity. The second one is about martensitic transformation. So let's try to see the first one. So this is done by Farid Abraham from IBM before he retired. So I have a tensile bar, and I just created two notches on the top and the bottom surface. And then when you start to apply a tensile load, then you can see you can generate a plume of dislocations. So you're going to have an avalanche of dislocations. So occur very fast, and then you start the work hardening and so on and so forth. So this is the real martensitic transformation. And so the paper is published in Nature about 10 years or so. And you can see that this is doing thermal cycling. When you start a transformation, the martensitic transformation start from this corner. And then after they start, you have this avalanche effect. It just go very quickly. You're going to have a strain avalanche or strain burst. So for dislocation plasticity, the transformation plasticity, and also for twinning plasticity, all of them share the same nature. They are driven by this long-range elastic interaction, and then they lead to a very strong autocatalytic effect. So for a lot of applications, we want to control those processes. From dislocation plasticity, over the years, we have developed a lot of strategy. How do we design a microstructure and then try to control the strain avalanche during a plastic deformation? But we actually, for phase transformation, we haven't utilized that much of the tricks we learned for dislocation plasticity yet. So today, I can focus on mainly on the martensitic transformation. And so let's see, the first topic, I'm going to try to focus on how we're going to regulate martensitic transformation by microstructure engineering to achieve controlled elastic and plastk deformation, controlled elastic and plastk strain release. And then I'm going to show a couple of examples. The first one, it can be how we're going to use point defects for a martensitic transformation, which is not very strong, which means the transformation strain may not be very large, say 2 or 3%. Then I'm going to show you how we're going to try to regulate stronger martensitic transformations if they have a transformation strain over 5% and can reach 10%. Then I'm going to show you how we're going to try to design nano or micron scale concentration modulations. Of course, we can always use dislocations and precipitate and then try to control the martensitic transformation. I don't think I have time today, but this is also a very, very interesting topic. We found there is an intrinsic coupling between the TWIP effect and TRIP effect in a lot of structural materials. You have the twinning-induced plasticity. You're going to have this transformation-induced plasticity. In particular, you can have a deformation twin, and then the deformation twin boundary can serve as a harbor for the structure transformations. So by doing so, you can really realize a lot of interesting properties I'm going to show you along the way during my talk. So during those study, actually, we learned a trick, all those tricks, point defects, that's solution strengthening, extended defects, that's all different kind of work hardening, precipitation hardening, and also grain refinement. So we learned all those tricks from the dislocation plasticity. But now, by doing so, we developed some new idea, and we want to apply back to how to regulate the dislocation plasticity as well. So I'm going to show you one example. How can we design hierarchical or gradient precipitate microstructure, and then try to push simultaneously the strength and ductility of those structure materials. So during my talk, I think if you have any questions, and then feel free to interrupt. I prefer some discussions and make sure actually you guys are with me and concentrate on my presentation. So if you look at titanium alloy, which is a typical structure materials, but it's not just structure materials in the common sense. It is also a structure materials in human body. So whenever you have whatever hip joint, kneecap need to replace, then right now, probably 90% you can find that's a piece of titanium alloys that's going to be used. And for metal implant, the big problem is the mismatch between the elastic modulus. First generation of those implant is stainless steel, which is even worse than the titanium alloys. The elastic modulus is about 200 gigapascal, and titanium alloys is over 100 gigapascal. If you look like the human bone, that's only about 20 gigapascal or lower. So if you have a large elastic modulus mismatch, the problem is that the load is mostly taken care by the metal implant, and the bone doesn't bear much load. And we know the bone need to regenerate. You need to give some stress stimuli. So if there's no stress stimulation, the bone doesn't regenerate. So it causes a big issue in this case. So people have spent a lot of time trying to develop very strong metals, but with very low modulus. But this creates a problem. So ideally, we want to have 1 gigapascal strength, and that's going to give us the optimal property we need for the implant. But at the same time, we want to have 20 gigapascal modulus. So this creates a dilemma, because if you are familiar with the physical metallurgy, we know the materials yield at 1/100th of its ideal strength. And the ideal strength of a metal is about 1/10th of the shear modulus. So if you require a yield strength 1 gigapascal, you want to have a 20 gigapascal modulus. So this is equivalent. You require the metal is going to have a yield strength which is about 50% of its ideal strength. So that's almost impossible for metals. And so we cannot simply use the intrinsic elasticity and try to design those kind of alloys. So we have to try to utilize what we call pseudo elasticity, which is the structure transformations. So I'm going to show some examples. How can we tune the martensitic transformation? As I showed you in the movie, is a very sharp, strong first order transformation into a continuous transformation, make it linear elastic, so we can use the low modulus and buy the transformation and to meet our requirements. So if you have a relatively weak martensitic transformation, for example, if the application only require about 1 or 2% of recoverable string, then you see I can use, say, point defects, just like a solution strengthening in the regular metallic alloys. So in this case, I just show you some very simple phase field simulation. So we have a certain amount of point defects. So if you have nickel tie, you put extra nickel into your system. So nickel tie is B2. If you put more nickel in it, you're going to create some anti-site defects. And then this is the diffusion of the defect concentration in a system. Then you can calculate, you put the defects, they have different atomic size. You're going to create a lattice distortion near the defects, and you can calculate the stress field in the system. When the defect concentration exceeds certain critical concentration, you'll be able to see that the stress field in the system percolate. And then if you buy that, you're going to see that when the stress field starts to percolate, then you're going to change significantly the behavior of the martensitic transformation. So here we have the system without those point defects. Then you see this is austenite at high temperature. Let's see, I can get a better pointer. So this is the martensite at high temperature. When you go to lower temperature, when you pass the critical temperature, boom, your system transforms from austenite into martensite within a very narrow temperature range. This is a very sudden transformation. That's actually the nature of martensitic transformation. Just like the movie I showed you. If you start to add point defects, then the picture starts to become a little bit blurred. But if you don't add enough, here you still have a clear transition between austenite and the martensite. But when you add more and more, say for example, in this case, it is really hard to tell when the transformation start and when the transformation finished. So if you look at the property, if you have just the pure system without the point defects, so in this case you have 50-50, nickel and tie. So this is the transformation, how the transformation occurs. All right, so you start to cool the system, start with austenite, cool the system. When you pass this transition temperature, you just jump and then you form the martensite. Same thing upon heating, the martensite just transform quickly into austenite. So this is the typical hysteresis for a first order transition. It's similar to solidification. You go from liquid to solid and solid to liquid. But if you dope iron here, so in this particular composition, you see the transformation. This is volume fraction again, and then there's a temperature normalized by the T0 temperature. That's the temperature you have. The martensite austenite has the exactly same free energy. Then you can see the transformation occurs within a much broader temperature range, number one. And number two, the transformation occur very gradually. They start much early on at a much higher temperature. In order to complete the transformation, you have to go to very low temperature. If you look at the stress strain curve, you can see that you can have a large hysteresis loop in this case. And then in this case, you have this very narrow hysteresis loop. It's almost like a linear superelastic. Pay attention to the slope. So this is the elastic modulus, and this is intrinsic elastic modulus of the austenite. Here, this is the pseudo modulus. You see, this has become smaller compared to this one. So point defects, doping, or engineering can really turn those type of martensitic transformation. It's just a typically first order into a continuous one. So this is for the point defect doping. We use some phase field simulation that's kind of phenomenological. You can actually use molecular statics, and you can calculate the stress field created by anti-side defects. So then you can convert the atomic scale stress you calculated into the continuum one. Then you can use this stress field from the molecular statics calculation as an input into phase field simulation for real systems. So that's what we did. So you have, this is the first case. And again, if you have a small amount of those point defects, you have a sharp transition from austenite into martensite. And then when you gradually increase the point defects, when you reach the critical values, the transformation become really, really continuous. And then here is the volume fraction as a function of the temperature. You have beginning a sharp transition, and then when you start to add more and more of those point defects, you see the transformation really become a continuous. So this is a kind of theoretical proof. Of course, those kind of calculations is kind of motivated by the experimental observation of this particular phenomena. People call it a strain glass system. So those kind of modeling work offered a very deep theoretical understanding about what's going on during the so-called strain glass transitions. So, but from those simulations, we also notice one important fact. For a martensitic transformation that has relatively small transformation strain, 2 or 3%, then you can do this by point defects. But if you have a martensitic transformation, like in nickel tie, you're going to have about 10% of the transformation strain. Then point defects is not strong enough. Then we need other type of defects. So that's going to lead me to the second topic, that's the extended defects for stronger martensitic transformation. So in this case, I'm going to go first about the concentration modulation we introduced, and then go quickly about the dislocation and precipitate. So this work is kind of motivated by the strong dependence of the martensitic start temperature on niobium content in this particular beta titanium alloy. And if you look at the stress-induced martensitic transformation, the critical stress to start the martensitic transformation, it's also a strong function of niobium content. So the idea is, if you have such a dependence, if you can create such a concentration modulation in your system, and you have a certain wavelength and amplitude you can control, then you can make certain local area. You're going to have some of the materials, you're going to have martensite, it's metal stable or stable at the testing temperature. Then when you move away from those regions, you're going to have the materials is going to harder to transform into martensite. So if you look at the microstructure, we can develop those kind of microstructure by spinodal decomposition. Then you're going to have niobium lean and then niobium rich. So that's you're going to give those different transformation temperatures. So in this case, the transformation may start at these regions, and so basically you're going to have those regions. You're going to have much higher transition temperature. But when the transformation start, so this microstructure look like an onion ring microstructure. So within the core, you start the transformation very easily at a very small stress level. You're going to transform into martensite, but the transformation stops because the next layer is going to need a higher stress to transform. Then when you increase a little bit of the stress, you transform a second layer. However, it's confined by the third layer, and the third layer requires a little bit higher stress to transform. Then you need to apply higher stress to induce the transformation of the third layer, and so on and so forth. So if you can do so, you can really convert this square-like hysteresis loop into this linear elastic and almost zero hysteresis loop. And the modulus, this is the intrinsic elastic modulus of the austinite. Well, you can see now this is pseudo modulus could be many, many times lower than the intrinsic elastic modulus. So this is the idea. And then, of course, we try to test the idea. And we use the phase wave simulation. We design the microstructure modulation. We have some experimental feedback in this system about the variation of niobium content. Then we did the simulation. So this is a very simple comparison. So we have this uniform system without the concentration modulation. This is the system with the concentration modulation. This is the starting microstructure for the transformation for the first cycle. When you apply load, the martensite transformation will occur in a uniform system and also in this nanometer scale concentration modulated system. This is the microstructure after the first cycle. The uniform system after first cycle, you can stay as a uniform austinite, and then the concentration modulated system after the first cycle, you're going to have residual martensite, which is stay as a stable. It's not going to transform into back to austinite, as I showed here. That's the pocket, which is going to survive, and then those are going to stay. And then during the second cycle, those ones are going to serve as the stable martensite embryo. They are ready to go. You don't need a nucleation anymore, and those ones simply just grow. And then they cannot grow too much because they are confined by the other martensitic domains. So by doing so, see, this is the straight strain curve for the uniform system for the first cycle and second cycle. So it doesn't change much. And those are the straight strain curve for the systems for the first cycles, because first cycles, this is all night. You still need nucleation of martensite in those locations, and then which give you this small strain avalanche, strain burst. And during the second cycle, you don't need this one anymore because there's no need for nucleation. You kind of eliminated entirely the hysteresis loop, and this basically give you those kind of stress strain response. So this is the in detailed microstructure evolution. So this is on the first cycle on the way loading, and then you can unload. That's the picture after unloading. You have residual martensite, and you start to load again. Those ones simply grow. It's similar to this reverse this process, and then you unload and you come back to this stage. If you load the third cycle, it's going to be similar as the second cycle, and that's what we show here. And if you put it all together, you can see the second cycle and third cycle just on top of each other. So this is the first thing we saw. And then also, unfortunately, for this particular one, we have a strong experimental effort. And they show that in this materials, this atom probe data, we do see nanoscale concentration modulation. This is niobium content in the system. It's a change from 8% all the way to 20%. And then that's how they behave, the straight strain curve and within a very large temperature range, all the way down to 4 Kelvin, you show this pseudo-elastic and linear response. So this is the one that is the ideal for us for bioimplant and also for a lot of other applications. So that's the first example. So now the question is, how about if you don't have the kind of concentration modulation produced by spinal decomposition? What are you going to do? Like in nucleotide, we don't have such a spinal decomposition. Then what you can do, you can try to solder a film with a very fine scale concentration modulation. So of course, this is easy. It's very easily to do in a simulation, but it may not so easy in the experiment. So that's why we have the paper published, and then we try to see if this is going to encourage the people to go ahead and do the experiment. Here, as what we learned from the previous case, you will have a nickel-rich layer. Then this one is very hard to transform into martensite. Then you're going to have a very nickel-lean layer. And this one wants to stay as martensite, doesn't want to transform into austinite. And then you start with 100% of austinite of the film, and then you load at the first cycles, you induce martensite, the transform grow gradually, but you can never transform 100% because this is a nickel-rich layer. You stay as austenite, and when you start to unload, the austenite simply fight back, and then the martensite recede, and then but you always have a layer of martensite stable when you start the second cycles, and then the process repeat. So after the second cycle, you don't need a nucleation of martensite anymore. Then you're going to create this kind of stress-strain scale, a kind of a stress-strain behavior. And then, so by design, those are two types of metals: concentration gradient. This is beta titanium alloy. This one has been validated by experiment. You can get the modulus down to this low, and then for this alloys, actually we can get the modulus down even lower. But this we are await for the experimental validation. So this is about the design, the concentration gradient. Of course, you can utilize nano-precipitate in a system, and then this has a lot of shape memory alloy systems. You have precipitate, nano-precipitate also create a local stress gradient, a local scale. You also have a stress field, and then you can change the transmission behavior from very sharp ones into gradual ones. So that's about the precipitate. Of course, you can use dislocation as well. So this is the one done by my former advisors group, Armin Kachurian. So they showed that if you have a dislocation structure, then you can also do the same purpose. You can induce the martensitic embryo, and then they transform gradually. Then you can change the sharp first order transition into more or less continuous transformation. So that's basically the first topic. So by doing so, we can really change the behavior of martensitic transformation from sharp first order into continuous transformation. By doing so, you can produce linear superelastic ultra low elastic modulus. You can also have this Elinwa anomalies, which means that you can have a zero thermal expansion coefficient, or you can have an elastic modulus, which doesn't depend on temperature. And you can also make a very progressive trip effect. So you can have a very large uniform elongation. And in this case, you can produce materials with simultaneously high strength and high ductility. So by doing those studies, we actually learn a lot. You can utilize different kind of microstructure to regulate the martensitic transformation. As I said at the beginning, the martensitic transformation is very similar to the dislocation plasticity. So now say, why don't we use some of ideas we learned here, and then we try to come back to apply to the dislocation plasticity. So I'm going to show you one example that we learned from those exercises, and in this case. So over the years, people have tried to regulate plastic activity, dislocation activities by grain boundary engineering. So this is typical examples by Close group. And so they basically use electrodeposition. They can create those nanotwins in copper. And they showed if you have those nanotwins within those big grains in copper, you can really push both the strength and ductility to a very high level. And you cannot be achieved by this coarse grain copper or just nano copper alone. So this is a pretty big achievement, and that's why they are able to publish in Science. And more recently, people have proposed a so-called gradient grain structure, that if you do really push the ductility versus yield strength curve from this shape into this shape. So for a lot of engineering applications, in particular for high temperature, the single-phase materials is not good enough. So you need multi-phase materials. You need a second phase to strengthen. So you can, this is a typical microstructure observed in nickel-based superalloys. You can develop easily a bimodal microstructure. You have this large precipitate, you have small precipitate. So our idea is, can we design a precipitate microstructure which follows the grain we'll try to engineer, either hierarchical or with a strong gradient? So this is the exercise we did. So we used this binary system for proof of concept. And so we try to utilize the phase diagram of this system. You have a miscibility gap. So at a high temperature, you have a miscibility gap in the beta phase. So if you, sorry, this is a low temperature, high temperature, you have a miscibility gap in the beta phase. If you do a common tangent construction, then this solid lean, solid rich beta phase, that's the equilibrium phases you have. So at 650, you can develop this kind of microstructure. The solid lean area, when you quench to lower temperature, you're going to cross, is very close to the crossover point of the free energy curve. So in this case, then you're going to have a new transformation mechanisms get involved, which give you very fine alpha beta microstructure. And then you will, in this case, this is the spinel microstructure at a high temperature. Then when you anneal at a low temperature, you're going to get those kind of microstructure. So if you are familiar with the, this is the transformation mechanisms. So if you're close to this crossover point and then all to the other side of this crossover point, the transformation is going to occur by congruent transformation. There's no need to change the composition. You only need to change the structure from BCC to HCP. So this is a much faster process, and you have smaller nucleation energy barrier for this process. You can generate a lot of alpha phase embedded in beta. So this which give you the very fine microstructure. Then the composition gradually evolve into equilibrium. So this new mechanism people call this pseudo-spinel mechanisms. So by doing so, you can actually produce those very interesting microstructure. If you are familiar with the microstructure of titanium alloys, you have globular alpha and you have alpha plus beta. This is called a bimodal microstructure. What you can do by these mechanisms, you can create an inverted bimodal microstructure. We know BCC is more ductile and plastic deformation friendly compared to HCP materials. So we think that this inverted bimodal should have a better ductility and strength as compared to this regular bimodal microstructure. So right now we try to do the experiment and then try to produce those microstructure and try to test the property of the alloy system we have. And again, if you don't have a spinel in the system, you don't have to rely on spinel. You can try to use the current technology to produce the concentration modulation you want with the right wavelengths and also amplitude. Then you can develop very fine microstructure and then coarse microstructure, fine microstructure, and then coarse microstructure by invoking different transformation mechanisms. You can also use other ways, and here interdiffusion you can do by 3D printing. I can show you two examples we exercised here. And if you look at the first one, so we can produce by interdiffusion. You start with multilayers, you do annealing, you can convert a square concentration wave into this sinusoidal wave. If you do annealing, then you can have this kind of microstructure develop very coarse alpha plus beta, very fine scale alpha plus beta. So recently we did an experiment. This is also titanium alloy, and we know inherently you have the concentration modulation during 3D printing because you cool too fast. You cannot allow that's not allow the system to homogenize. So naturally you have this inherent concentration non-uniformity. But if you try to do in situ alloying in the 3D printing, then you can really make the concentration modulation down to micrometer, micron scale. If by doing so, we are able to increase both the strength and ductility of the material. And in titanium alloy, if you are familiar with titanium alloy, you're going to immediately realize that this is significant because in most of the titanium alloys, you don't have much of work hardening at all. You can either flat or you can after yielding, the curve goes down immediately. But here you have a very significant work hardening, which allow us to achieve very large engineering strain and the uniform elongation, tensile strength combined. So we have a significant improvement against the existing titanium alloys and processed by different processes. So this same idea can be applied to dislocation plasticity as well. So the major takeaways, so time is over. So basically in crystal, if you think about plastk deformation, which can be carried by, of course, dislocations, but the deformation twinning and structure phase transformation, they are also the major plasticity carrier. So the structure transformation is unique. It can be plasticity carrier, can also be elasticity carrier. So if we can try to combine to utilize those different processes, then we can achieve a very interesting property that you only see if you just try to utilize one process. And in most cases, they are strictly coupled together. And those processes, they share the same nature. And that's the autocatalysis and strain avalanche. If you can have a smart design of the microstructure, which allow you to precisely control the strain release, not by an avalanche, then you can enjoy a lot of interesting properties of the system, as the example I showed you. So you can control the strain release during martensitic transformations by point defects, nanoscale concentration, modulation, dislocations precipitate. And I showed you, if you're doing so, the local stress field or the concentration modulation is going to confine the phase transformation at a local scale, and they're going to happen, the transformation occur a little bit at a time. In this case, you can have a smooth transformation. And if you can have a smooth transition, if you can control the strain release, then you can tailor the material properties. As I already said, you can produce ultra-low elastic modulus, linear superelastic with almost zero hysteresis. You can find a lot of applications for this property. You can have a very progressive trip effect, which give you an excellent work hardenability and also prolonged uniform elongation. This is also very important for material design. And then, of course, you can have the Innova anomalies. I didn't have time to show today. All right, so you can also control strain release for dislocation plasticity by hierarchical and gradient precipitate microstructures. So nowadays, for the advanced material processing technology available, it's no problem for us to create such kind of a hierarchical and the gradient precipitate microstructures. So you can let your imagination run wild and try to design whatever the microstructure you need, and you can try to get the unique properties that you expect. So with that, I'd like to stop, and I'd like thank you for your attention, and I would like to answer any questions you may have.
Thank you very much, Professor Wang. So, yeah. Any questions from the audience? It's really interesting talk. Okay, so while everyone else is thinking about, so I have a quick question. Because on the end of the point defect doping, there's a plot which is about the volume fraction of martensite versus temperature. And we can see like, the next one. So the last two compositions, whereas you have more, if x equals 2 and 2.5. So these two looks quite similar with each other. Is there any threshold or critical like point for the concentration?
Yes,
effect.
That's a pretty good question. So usually for the disappearance of any of the signature of a sharp transition at a critical concentration, in this particular system, the critical concentration is around 1.25. So when you bypass 1.25, you basically, this sharp transition disappeared. So this one is just on a verge. And so if you exceed 1.25, the transformation just go smoothly. Okay. And so here is 1.25. So you still have a little bit of this internal twin structure. So when you bypass this point, that's what you have. And we expect that 1.25, a little bit beyond 1.25, that's to be the critical defect concentration you need.
Okay, thanks. So do we need any I? Like what's the, sorry, so maybe I didn't catch it. So what's the effects of I alloying in this case?
Oh, this is I think for this particular system, you can either add extra nickel, and then you create anti-side defects, or you can add iron in the system, which is it's a similar effect as the anti-side defects.
Okay.
So iron can occupy selectively at the nickel sublattice in the B2 structure, and then going to create a local lattice distortion, which give you a similar effect as if you add more nickel exceed 50.
Yeah. So like as always, just from an industrial perspective, like for these two, is there a better way, or which is iron is essential, or is nickel, is pure titanium nickel is a better solution?
I
think impurities in some other alloys.
You can dope different kind of impurities.
Yeah.
It's not necessarily has to be iron. So this is just two experimental systems people have tried.
Okay.
So people put more nickel in this system, and then people add iron in this system. And in both cases, they found the very similar effect.
Thank you. Thank you very much. I think Elon raised his hand, please.
Yes. Thanks a lot, Professor Wang. It's very impressive talk. Actually, I've got some questions about the your talk about the increase of yield stress or flow stress of titanium alloys in the sort of ending part of your talk. So I'm just interested first whether this phenomenon is general for all the majority of titanium alloys, because the flow stress is very key performance for the application of titanium alloys. Second, how is that possible, or would you think it's possible to quantify the increase of the yield stress or the flow stress? For example, here you are showing ice cast the yield stress about 900 something microscope, but as printed, it's about it's increased significantly to over 1,200. So would it be possible to quantify, or to understand how much would it be to achieve? Because during the application in aero space or applications, it's very crucial to have the property more accurately determined from the manufacturing, or if we can know the properties, we can have a better application scenario. For example, to increase the temperature, something like that one. Just some questions about that.
Thank you for the question. This is a very good question. Actually, in titanium alloy, people have tried to create this large-scale concentration gradient by, say, the laser deposition, the lens system. Actually, they can achieve this work hardening, but usually the flow stress the maximum is about around 400 or 600. It's pretty low. And the uniqueness for this one is by 3D printing, you can control the concentration modulation really at a small scale, the micrometer scale.
Okay.
And by doing this in situ alloying, and we were also able to control the grain size at the micron scale. And so the both effect helped us to push this curve all the way up. And by have a fine scale concentration modulation, you're going to have fine scale this precipitated microstructure, and then you're going to have this prolonged the trip effect, the transmission induced the martensitic transformation in the system, and plus the fine grain size. I think all three factors helped us to push this one. Of course, you're going to have these solid solution strengthening as well, and so to deconvolute each of those effects, we need some effort. So right now we are doing more detailed characterization to see the details of the deformation microstructure and try to see basically what's the dominant contribution to this this high flow stress and also high uniform elongation.
Yeah.
Yes, Zhang, please. Oh, sorry. You please unmute. Hi, Zhang.
Yep, sorry. Yeah, thank you very much, Unjun, for very nice talk. That's very impressive work. Also have follow-up question on that titanium alloy. So my understanding is you need to use kind of like in situ not alloying, like a lens technique to manipulate the microstructure. Also read number of papers from other groups. They want to do not rely on kind of in situ alloying, but basically just like a composition and play with kind of regime of trip and trip for titanium alloys, and that would be make probably more wider adaptability to the additive manufacturing community. Have you thought about to combine the way we can regulate the microstructure, but also we can tailor, the composition, because that affects like a stacking force energies, and that would affect the trip and trip behavior. Have you think to combine that two approaches together to increase greater flexibility in controlling the microstructure and also kind of manipulate trip or trip behavior in the titanium alloys?
Yes, actually, in titanium alloy, we are learning a lot of tricks from steel industry, and the trip and the trip effect has been very, very hot in those days. I think I don't have time to show today for the actually this is a very interesting part for this kind of a study. In titanium alloys, and it doesn't matter if it's a nickel tie or if you have a beta titanium alloys, it's very interesting if you can combine the trip and trip effect. So you can develop a deformation twinning, which in the BCC phase. Then so for this particular system, you develop this deformation twinning in the BCC state. And what we found at the twin boundary of those twinning in BCC, actually you have a layer of alpha double prime of martensite. So we analyze and we try to understand why that is the case. And then we did some crystallography analysis. We found this is very, very similar to the extended core structure of a dislocation. So in this particular system, beta tie, if you have a deformation twin boundary between two beta grains, across the twin boundary, you have to have a layer of alpha double prime of martensite. So in this case, this is the behavior of the materials become really interesting. So you have this B19 prime martensite. This is in the sheet memory alloys. So this is in the titanium alloys. If you have a layer of alpha double prime martensite already there, if you start to apply a load, then those martensite is going to grow, and which allow you to have a very prolonged trip effect. So this is why we have this beta or metastable beta titanium alloys. You can achieve very interesting property, and it's because this intrinsic coupling between deformation twin and the martensitic transformation. So what we try to do now is try to engineer those kind of microstructure on purpose, and then try to achieve certain properties. So the first example we tried is to coat roll a nickel tie. We developed a lot of twin boundaries, and then we find the martensite between two B2 grains, and then we test the properties. We did find this very interesting properties. You change the transformation behavior into this, as the one I showed you earlier. You have this pseudo-linear elastic, almost zero hysteresis, and very low hysteresis, and then you can achieve pretty low modulus. So we are doing this one for metastable beta tie, and for metastable beta tie, and you can do you can try to induce if you can induce a lot of deformation twin in the in the BCC phase, and I would anticipate a very interesting property.
Yeah, thank you very much. That's very nice. I just have another follow-up question. So if you think about like in additive manufacturing, if you go to kind of like a laser powder bed, the cooling rate is very high, and normally we see a lot of martensite already because of rapid cooling. Do you think that we need to use more kind of like a beta stabilizer to get kind of metastable BCC despite of the rapid cooling? Otherwise, if you transform a lot to from BCC to martensite, we have very high strength, but we could lose a lot of ductility.
Actually, you are exactly right. That's exactly what we did for this this last example I showed you, because the work hasn't been published yet, so I didn't show the details. So that's basically the idea we used. We tried to make more beta stabilizer, and we want to have a very non-uniform distribution of the beta stabilizer at a very small length scale, utilizing the whatever the unique features provided by this 3D printing. And this is the powder bed laser, and we can achieve this property change. That's exactly
yeah.
It's exactly the idea you mentioned.
Mm. yeah, thank you. That's brilliant. Yeah.
So this is kind of learned from the concentration modulation for regulated martensitic transformation we had in the sheet memory alloys. So we try to use in those systems. And then we are also working on steels, and try to come back to steels and try to see if we can design this is such a small scale concentration modulation, and then try to make the combined trip effect there.
Yeah, that's amazing work. Yeah, thank you very much. We should always need to start from steels first and explore other alloys, and probably hopefully can go back and to improve steels as well.
Yes.
Yeah, thank you.
You're welcome.
It's very nice. Any other questions? All right. Okay. So also it's already 2 o'clock. I think it's time is up for today. And thank you again, Professor Wang, for giving us such a great talk. And we hope to. So any of you, if you have any questions, you can send him an email. I think this recording will be posted later to share between us, and maybe some of this recording will be posted online as well. Okay. So thank you guys, and thank you, Professor Wang.
Thank you. And could you send me the link as well?
Yeah, I will send you the link before we publish it.
All right. Thank you very much.
Thank you very much. Thank you.
Bye-bye.
Bye.